And so with that, I'm going to introduce our first speaker, Dr. Andrew Gray, which I'm going to read his bio because I don't know it by heart, but he's an assistant professor at Watershed Hydrology at the University of California at Riverside. He completed his doctoral work in hydrologic sciences at the University of California, Davis, go Aggies, where he focused on fluvial sediment dynamics in small mountainous rivers. Dr. Gray is now building a research group to investigate the role of fluvial sediments in determining water quality and fluvio-geomorphology with particular interest in coastal environments and role of humans and climate in controlling sediment production, contamination, and transport dynamics. Andrew, it's all you.
Thanks, Ali. Oh, thank you. Well, it's nice to be back up in Sacramento. I lived here for about 5 or 6 years while I was at Davis. And so I guess I'm going to zoom down from speaking about data science to more kind of beating the drum for better data collection in the first place. And so my talk today is about non-stationary suspended sediment dynamics. And really, in the end, what I'll be arguing for is sort of rethinking the way we collect sediment data. So just to kind of walk you through it, first I'm going to argue for the fact that fine river sediment is really a master variable in aquatic systems, and that we see lots of natural variability and human influence variability in sediment abundance in river systems, and that this varies in orders of magnitude within a system and across systems and over space and time, and that really we also see non-stationary dynamics within the abundance of this sediment in rivers, and now that this can do a lot to kind of undermine watershed management that's based more on snapshots at a given place or across a watershed, but over very limited time spans. And in the end, I'll make a few suggestions on how we can deal with this. So just to start us off today, I'm really just speaking about fine sediment. So sediment that's transported primarily in suspension within rivers. It's maintained in suspension through turbulent fluctuation and not through direct interaction with the bed of the river, unlike bed load. And that the finest fraction of the suspended load is really, it's not really controlled in its abundance in terms of the tractive capability of the flow field, but rather by supply limitation. And for this reason, when we get to the finest fraction, we don't really see a concentration depth profile, although we do with coarser material. And I'll circle back to some of these phenomena as we go through the talk. And so really the fundamental tension of sediment in rivers is the fact that on the one hand, all natural river systems transport sediment, right? And it's really fundamental to the biogeochemical cycling of aquatic systems and coastal environments and really global scale biogeochemical cycles such as the carbon cycle. And it's really critically important for the maintenance of geomorphic components of aquatic systems, particularly coastal wetlands, which in most cases require a large mineral influx of fluvial sediment in order to keep up with sea level rise. On the other hand, with human interaction across the landscape, which is ubiquitous, particularly in the developed world that we live in, many fluvial systems are experiencing an overabundance of sediment or a shift in sediment quality that fundamentally impairs many of their services to humans and the aquatic environment. And this includes impacts on physical habitat, direct impairment of organisms through direct interactions with fine sediments, as well as a whole array of surface-mediated transport of contaminants, hydrophobic organic contaminants, heavy metals, et cetera, that also impair water bodies. And a really great example of this, spatially distributed across one watershed, is the Sacramento-San Joaquin system, where on the one hand, in the coastal regime, down in the Bay Delta, we really see wetlands that require fine sediment to keep pace with sea level rise. And we have a big issue of legacy contaminant of sediments in the channel bottoms there. That also require new influxes of quote-unquote clean sediment in order to keep them from being resuspended and causing water quality problems. And this is all work that's come out of the USGS and others. But on the other hand, in the interior, we have this big restructuring of source due to a lot of the damming that's held back a lot of the clean sediment resources from the interior. But also largely impaired physical habitat for the remaining sematids in the system, where we really need cleaner gravel, coarser streams, and fine sediment plays a huge role in impairing that in some cases. And we have all these other direct human uses that are overlain upon that, where fine sediment and sediment-associated contaminants are a huge issue. So to kind of pull away from some of those problems and think about how we actually monitor sediment in systems, largely we do a dipstick of sorts. You know, most of the sediment data that's out there is either turbidity data with no suspended sediment concentration information attached, and certainly no discharge attached with it, which gives us an idea of the abundance of sediment at that particular spot in a fluvial system at that particular time. But when it's divorced from what I would call a more dynamical or flux-based context, it severely limits the kinds of questions we can answer with those data. And so from a flux-based perspective, what we really need is discharge data at a minimum. And of course, then ideally, spatially distributed data sets and longer time series, but we'll go into that a little more. When we have discharge data, then we can start to think about sediment dynamics, right? Because really, in the end, remember, fine sediment isn't limited by the tractive capability of the flow. So when we're using discharge, for example, to describe how much fine sediment may be in a river, what we're really doing is using discharge as a proxy for the same internal and external forcing factors that are conspiring to supply the channel with fine sediment. And this is very common, it's just another rating curve. We do an empirical bivariate relationship to describe something that's kind of hard to monitor, sediment concentration, by something that's relatively easy to monitor, which is discharge. And by employing these concentration discharge rating curves, we can explain some of the variability, right? So this is the fine sediment discharge rating curve for the lower Salinas River, which is like a 10,000 square kilometer watershed, pretty typical of the coast, the different systems draining the coast ranges, where we have something on the order of 4 orders of magnitude of sediment concentration variation across the discharge domain. This is pretty typical. If we fit a rating curve relationship to this, we can knock out about 2 orders of magnitude of variability just by knowing the discharge. We can say, oh, okay, well, now I can estimate what the concentration is, but it'll still, in this case, be about plus or minus 10x, right? So you still have 2 orders of magnitude of concentration that you can't confidently say that you're predicting. And so this is where the issue of non-stationarity comes in. This huge variance around the rating curve is there for many, many, many reasons, and one issue is the fact that the system is non-stationary. And we'll get back to that. But if we take this rating curve and we convolute it by the discharge frequency probability function, what we also see, and this is work of Farnsworth and Warwick from the USGS, in this case, what they illustrated is essentially what percentage of the record ends up contributing 90% of the sediment that's moved through these systems. And you can see in the north, it's about 5 to 10% of the record. Once you get down to SoCal, where I live now, it's around close to 0 to 1%. So what we're dealing with here in California in these small systems are highly episodic systems in terms of water, as you all know, but even more so in terms of sediment flux, right? And so we're really dealing with rivers that, with the sediment that's moving through them are effectively transported by rare high magnitude events. So if we back away just from thinking about, okay, I have this data set and I'll try to maybe predict how much sediment's moving through a river over the entire, say, the time domain of when I was sampling, or the entire domain of time of interest, and to extrapolate beyond that. If you slap a individual rating curve onto that whole thing, essentially you're assuming that the system's stationary, that relationship between discharge and concentration stays the same over time, right? A non-stationary system where that relationship changes in a time-dependent fashion, and here it's just illustrated kind of generically as late and early. This can be one of the major issues that ends up impacting all this variance we have around these rating curves. And we see this at a huge range of temporal scales. But in the interest of what we're focusing on here in terms of watershed planning and water quality issues, really my focus today will be talking about event to interdecadal timescales, and those are really sort of the timescales where we have actual data on suspended sediment anyway. And so I'm going to march through a couple of different examples of where we've seen this. This is work by Warwick and Goni and others up in the Eel River. In this case, again, you have another 10,000 square kilometer basin that experienced this massive flood, the Christmas flood of 1964, which highly aggravated sediment supply to the Eel River. And what they found is that it's actually been rebounding from that event ever since. And so we see this interdecadal, and here this is the residuals of a suspended sediment rating curve plotted. You see this interdecadal decrease in sediment concentration over time when you correct for this relationship with discharge. So basically, you have an event scale disturbance that leads to an interdecadal scale rebound in the supply condition. And of course, we'd never know that, unless we actually had interdecadal scale data, and we generally don't. Here's another example of an event scale disturbance with sort of more interannual implications, but that can then be compounded to millennial scale considerations of sediment flux. But in the Arroyo Seco watershed, which is or sub-basin of the Salinas River, there was a complete burn back in 1977, and then again in 2008. And the USGS was doing sediment sampling there in 77, and the group I was working with in 2008 was also happened to be sampling. So we just had this sort of lucky opportunity to compare the response of this system across two different similar burning events. And what you end up seeing is that in 1977, there was about 100x response from the pre-fire conditions. So there was a aggravation of sediment supply and flux from the system on a scale of 2 orders of magnitude. But in 2008, it only about doubled. And the difference there wasn't the fact that, it had burned completely in both cases. The difference was the sequence of precipitation that happened after the wildfire, which I think makes sense to most of you, right? In 1977, there was something on the order of like a 10-year rainfall intensity event, and in 2008 it was basically average. And it was that sequencing of disturbance and rainfall that really led to this this massive flux of sediment out of the system while it was in a very vulnerable state. And then if we zoom down to just the event scale, so if you're looking at a suspended sediment record, even just within the rise and fall of a hydrograph, we often see hysteretic relationships. So you don't necessarily see the concentration just marching up and down the rating curve, but oftentimes it'll do positive loops, negative loops, fishtails, all sorts of funky things. And that can be motivated by lots of different processes, one of which is the relative contribution of different hydrologic regimes, including base flow, storm flow, et cetera. So it's another non-stationary issue that has to be considered strictly at the event scale alone. And then, in other systems where we have enough data to kind of dig into them a little more deeply, such as the Salinas, where we had a pretty good suspended sediment record that we had also augmented, great discharge record and some other things. We're able to go through and query those data in thinking about the antecedent conditioning of that watershed purely on the basis of the record of discharge alone for the most part, and using that record of discharge as an integrated representation of antecedent moisture conditions in the basin. And what we found is that at the event to sort of annual, semi-interannual scale, we had loading and flushing regimes. And I think a lot of you are probably familiar with that concept in terms of the first flush of a system and how that can move a lot of sediment and contaminants because we have this dry summer Mediterranean climatic regime. But if we look at how those loading and flushing drivers organize in a persistent fashion across interannual to decadal timescales, we found that drove the interannual to decadal cycles of sediment concentration aggravation or degradation in the system over time. But then there were also interdecadal trends that were going on that were probably aggravated or caused by changes in human operations in the basin. In the Salinas, there's a lot of agriculture, and changes in irrigation operations have probably actually reduced sediment loading. So this is a case of what's happening in pretty much every watershed, most likely, if we had enough data to start looking at it. The fact that we have a mosaic of many, many different processes that are driving these non-stationary behaviors. So in the end, what we have is an issue of high variability that's not stationary in time, and a lot of watersheds that are mostly undescribed in this context, right? So there's probably about 250 watersheds draining into the Pacific Ocean on the continental, from the continental western U.S. Only about 23 of them have 10 plus years of suspended sediment data that's dynamic in context, that actually has associated discharge data. So, most of those data sets are short in duration. There's a lot of other kind of, 1 year, 2 year data sets. All of them are pretty much sporadic for the most part and quite low resolution. There are a few high resolution short-term data sets that are out there. But the thing to remember is that, when you have these little snapshots of what's going on in these systems, remember they're very episodically driven. So most likely we're missing a lot of the real kind of main driving events that set the geomorphology of some of these systems, that have large impacts on sediment flux and redistribution through the systems, and also the aquatic habitats. And also, I'd like to highlight that we have almost no sediment composition and associated contamination data. There are a lot of data from river channels and channel banks in terms of the contaminant loading, but actually from suspended sediment samples that are in flux through systems, there's very, very few data sets out there because it's very, very difficult. You have to collect a lot of sediment and do a lot of work on it. And there are a few groups who've done great work there, but there isn't much. So in the end, the way forward, of course, you can't go out and collect all of this data all the time, and it has to be driven by the questions that you're trying to answer. But since a lot of the action, particularly a lot of the action in terms of the transport of sediment-associated contaminants, happens in the finest fraction of sediment, right, where we don't have to worry so much about this concentration depth profile and doing things in the full-on USGS fashion of doing depth-integrated and flow-integrated sampling. That leaves us open to using more automated fixed sampling methods like employing ISCOs and other things that have been around for decades. But there's an opportunity here to not only do more automated sampling of fine sediment, but pairing that with kind of easy, quick, and automated or semi-automated methods of collecting discharge data. Also, I think there's a lot of room to increase the amount of sediment-associated contaminant and characteristic data that's collected out there. And there are some groups that are already working on this. And really, you need to start with having the suspended sediment dynamic data and then add on these kinds of contaminant analyses, but the problem is you do oftentimes have to collect 10 to 1,000 liters of water at a time. But there are continuous flow options that can be employed in the field at this point, where that water can at least be fully or partially processed in the field, so you don't actually have to walk away with 1,000 liters of water, maybe just a liter. But at the end of the day, we know very little about the dynamics of the contaminants that are traveling along with these sediments, because their concentration isn't fixed on the sediment that you're sampling. It's also experiencing dynamism and non-stationary behaviors that are related to supply and active degradation and transport. Right? And so, this gets back to the next level that we can get to beyond looking at these patterns over time, is actually thinking about where is the sediment coming from, right? What is the source? Because that, in the end, is also driving what the composition is, which is a big factor when it comes to water quality. And there's many ways to start to approach that, including using, employing mixing models that are based on trace elements and also these contaminants that are of interest, but also employing things that are actively, naturally tagging surfaces and fine sediments throughout the watersheds, like fallout radionuclides that can be pretty easily analyzed at the lab scale using things like gamma spectrometers. And this can get us towards actually understanding erosion and transport processes in these basins, and really help to kind of bridge that gap towards a real watershed-based plan when it comes to sediment management. And so I think, people have been thinking about sediment in the context of water quality for a long time. It was one of the real early constituents that were recognized as severely impairing water bodies in the U.S. And people, I'm not saying have walked away from it, but it's been a pretty difficult one to deal with because of this variability. But to try to access this problem in a lot of systems, there needs to be some kind of recommitment to dynamical and flux-based monitoring. But there's also a lot of opportunities to employ emergent technologies, remote sensing, high-resolution surveys, which I didn't talk about, and some of these sediment fingerprinting issues. And really, in all cases, we need an explicit consideration of time, both in terms of these non-stationary dynamics, but also in terms of the particular questions that we're asking, and also this issue of how sediment moves through these systems. And something I didn't talk about at all, but something I think all of us need to think about, which is the fact that the response time of a watershed in terms of cutting off hill slope sediment supply can be much, much, much longer than the time of transport within the channel. And with that, thank you, and here are some references.